Much energy.
We did it in class.
Can they do what? That's the problem.
Can't they just do what we did?
Oh, they could just have engineer Kelly and Snigda, right? They have no problem. Shut up. Kelly doesn't appreciate that. I will not ever say another word about it for the rest of my life.
That's so much. We'll invest in next year.
No. I can just see Kelly coming at me with an axe. Not doing it.
Or today, I have to go all day today.
All right. So, Spencer, let's move down the rest of the way. Now, if we wanted to take this reaction and reverse it, we have water and we want to get water to split apart. We're going to have to use more than 2.06 volts with an external power supply, pushing the electrons back the other direction. Rather than the hydrogen oxidizing and giving electrons the oxygen, we need the oxygen to give electrons the hydrogen, so we need an external source for that. If I'm telling you the truth, and that matters a lot to me, I'm big on telling the truth. This with pure water will not work. You have to add some electrolyte to it just to make sure that the charges can flow between the two electrodes.
Watching Pedialyte for me.
I'm good. You go ahead and drink that. So I have a little demonstration I want to show you back there. That I've got some water, but the water has been spiked with some sulfuric acid just to provide some ions there so the charges can flow. I'll be careful.
Okay.
Tarun, come on back here.
Wow.
Oh, sit right here, Tarun. So everybody can see.
Dude, no.
This is our external power source, this big ugly blue thing that I'm talking about. So when you see, in my drawings, a box that says power source, this is it. It's got a negative and a positive terminal on it. The positive is on the left and the negative is on the right. Remember, the electrons are always flowing out of the negative terminal. So out of the negative is going to be this thing right there. The electrons we think are flowing this way. What does that make this compartment, the anode or the cathode? Electrons are flowing into it.
Anode.
Oh, I got both.
Oh, out of the source, so it's cathode.
The electrons are coming in here. That means reduction is going to be occurring over here. Cathode. That's the cathode. This is attached to the negative. This is attached to the positive terminal. The electrons are being pulled into the positive, making this side the anode. This is the source of the electrons from the solution, and then they're going to go like that. Out of the power supply, the source is the negative terminal. Okay. If I turn this baby on, now I've got the dial turned all the way down. You can adjust the voltage on it. And turn it on, you can see that the light turns on, so that this thing is working. But I need to turn the dial up to get some voltage out of it. Now if I turn it, you watch very carefully. I'm not going to turn it much. Nope, you see it move? It just kind of clicked a little bit to the right. Now I want you to look very carefully at these two. Now this is the real thing. That's platinum inside of there. Platinum is a nice, beautiful, silver-colored metal.
I thought you said it was too expensive.
Well, it
For a
came in the
real
thing.
thin leaf of platinum, we can afford it. For a bar of platinum, no, it's way too expensive. So these, I can't tell you how much these cost. They're a little bit expensive because they are platinum, but they're not unaffordable. But it's real thin leaf of platinum that's in there. I need at least 2.06 volts, so that's why I wanted to show you. This thing is kind of a crude dial. If I turn it up much more at all, you see it move more? So you can see that it's off to 0. Oh! Can you see anything happening in there?
No.
If you're close to it, you're going to see a real thin stream of bubbles coming up out of both pieces of platinum. It's bubbling. Now I'm going to, let's see, switch it down here. And I'm going to kick up the voltage a lot. I'm going to kick it up to about 15 volts. Just so that everybody can see it. Yeah. So now, hopefully, where you're sitting, you can see the bubbling going on from both of these. Now you notice that these did not start up all the way at the top. They started kind of down farther. But I want you to just watch this over time. Remembering that the electrons are coming out of here and then going into there. Do you expect both of these sides to go down at the same rate?
No.
Which one do you think should go down fast? Thank you, Michelle. Michelle, do what you just did. Thank you. Did you see what Michelle did?
Not even.
What were you looking at?
The equation?
Yes. And what does the equation tell you?
There's
As
two
much
most.
hydrogen as oxygen.
Yes. Very nice.
What did she say?
The same thing.
Yeah, but
Taking that reaction and going back the other way, the water is now changing into hydrogen and oxygen. That's what's going on in here. You get 2 hydrogens for every oxygen. That's what the chemical equation tells us. 2 H2O plus 1 O2. So that means that
the hydrogen will empty out before the oxygen.
the hydrogen is going to go down twice as fast as the oxygen goes down. So they're going to go like at this rate. Both of them are going down, but the hydrogen is going to be going down twice as fast as the oxygen. Now, do you see that happening right now?
Not really.
Yes,
but
a little bit.
What?
A little bit.
A lot.
A
I'm
lot.
on the ground looking up at an angle.
Is there stuff in here?
I'm sleeping.
I know. I noticed first hour that when I went up to the front of the room, you can hardly see it. You can look from closer. Bubbles. Everybody likes bubbles.
Does it bother you that some of the people flash?
No.
Okay.
Does it bother you that Tarun plays?
Never pull niggas for no apparent reason.
Which Tarun? Oh, this one? I used to.
There's multiple.
It just surprised me so much. All right, now check this out.
You're not out of
Are you able to tell that this one is the hydrogen, not just because it's going down twice as fast? How else would you know that it's the hydrogen? Because it's the cathode is the one that's gaining the electrons. It's going from H with a positive 1 oxidation number to H0. The electrons are coming out of the negative terminal into that one. We have hydrogen reducing. Very nice. Now, I wasn't planning ahead. I should have, if I would have been thinking, grabbed a test tube and held a test tube over here and collected some hydrogen and lighted it on fire. I promise that I'll burn hydrogen before too long. Yeah, I promise
Well,
I
you
will.
can do it now.
Not doing it now. We got too busy for now.
Do a Hindenburg.
All right.
We understand.
So anyway, yeah, we'll burn some hydrogen later. You'll notice the way this thing is set up. The reason that we have kind of an intricate setup like this in this middle post here is because as the water is displaced, it has to have some place to go. So it gets forced up this middle column into this, and this bulb is just there so that we're not watching this thing and water is spilling out over and getting our wires wet. You don't want wet wires when you have current flow.
What's so bad about wet wire? Oh.
That's probably why we didn't win for it. Our wires are probably
Yeah,
why.
let's just leave it. That's why.
So anyway, if I allow air back in here, the pressures equalize again. There they go, and they'll be the same.
So funny.
All right.
Wow.
That looks amazing.
Very EP. Very EP.
Drew, come back up here.
I'm not a puppy.
Aww. Spencer, let's continue. All right.
Holding my hair.
Now we just saw the electrolysis of water. Before that, we were talking about the electrolysis of melted sodium chloride, liquid sodium chloride. Now what we're going to look at is, what if you have water with sodium chloride dissolved in it? So you've got positive ions and negative ions there, the sodium ions and chloride ions. At the anode of a sodium chloride solution, there's 2 different things that could oxidize. The chloride ion can oxidize to Cl2, and the oxygen from the water could oxidize. Well, which one does?
The oxygen.
How would you know?
Because Cl can't react with the H. Wait, hang on, let me think about that.
You have to know the oxidation potential of both of these.
Okay, never mind.
Can you look them up?
C.
Find the oxidation of chloride ion on your paper. Chloride is pretty close to the top. Negative what? 1.36. Negative 1.36. Is chloride ion excited about oxidizing? No. A big negative number for the oxidation potential. It's not liking that too much. What about for oxygen and water?
Negative 1.2.
Oh, also not excited about oxidizing.
But it's more excited.
Yeah. I'll cover the next 2 lines. So our oxidation potential for the chloride ion oxidizing is negative 1.36. The oxidation potential for the oxygen in water is negative 1.23. So which one would rather? Neither one would like to, but which one is going to volunteer to oxidize? It's going to be the one that's more positive. Even if both of them are negative, one of them has to oxidize. It's going to be the one that's more positive. Spencer, one more line. Right there. This is worth writing down. I would, when I get to more positive, either underline, highlight, put a box around. That is important to recognize. Even if you have two of them that are negative, one of them has to oxidize. The one that does is going to be the one that's more positive. Or less negative if you like that better.
Mr. Moore. Thank you.
Sorry.
So if the cell if the oxidation potential of chloride ions like 0.14 greater than what it is now, it would do the thing with the
You would oxidize.
yeah.
Yeah. Yep.
Do the thing.
You said 0.14 greater. That means if that was negative 1.22
Yeah.
and that was negative 1.23, then the chloride would win. Yeah, and that would be the one oxidizing. Yep. Yep. We're going to do the same thing at the cathode now. Which one would reduce? What could possibly reduce in this mixture of salt water?
Na.
The Na, positive one, can reduce to 0. Anything else? The water, the hydrogen in water could reduce as well. Anything else in salt water?
Sorry.
Whoa.
My elbow hit the space deep.
Okay, Spencer, let's go down. 2 lines, 1 line, 1 line. Stop. All right, can you look up the reduction potential of the sodium ion and the hydrogen in water? Oh my gosh, that's the reduction of sodium. Negative 2.7. Is that going to be excited about
No.
reducing?
No.
No. What about the hydrogen in water? Water going to H2. Negative 0.83. Spencer, uncover the next two.
So
There they
if
are.
the whole reaction isn't happy, why are we...
I know this whole thing. Well, that's why you need that power supply, is to force the electrons in a way they wouldn't want to go. Yep. And you can expect this to happen a lot, all negatives, when you're having to decide what happens to the anode and what happens to the cathode. So between these two things, which one would rather happen? Who's going to volunteer? Neither one of them wants to, but it's like, okay, I'll do it. This second one is going to be the one. It's more positive. So at the cathode, the water will be reducing. So in both the anode and the cathode, it's going to be the water. What did the salt do then? Nothing.
Just stays there.
Salt is too stable as sodium ion and chloride ion that it's not going to prefer to oxidize or reduce. Everybody okay with that? Now, I got one last topic that we have to hustle along on. I don't want you to draw the picture on the next page, okay, because we got to save some time. Spencer?
Yeah.
So if we have this situation here, zinc compartment and an iron compartment, spontaneously the electrons should flow from the zinc to the iron. But I got the big blue monster here that's pushing the electrons the other direction. So that's causing these zinc ions, the electrons are coming in here, these zinc ions are going to be reducing to zinc metal. And then the iron plate here is dissolving as it goes to iron, as it's giving off its electrons. Now if the question is, how much zinc is going to plate onto this bar? How much zinc? We got to do a little stoichiometry to figure that out.
It's
Okay? I love it.
It's a good subject.
Very systematic. That's what I like about it. It's systematic. Know how the electrons are coming in here? If you have more electrons coming in, you're going to have more zinc that plates, yeah? Yeah. So, we need to do the stoichiometry to determine how much zinc is going to come in here. Spencer, let's go to the next slide. Okay. Now, in order to be able to do this, we have to understand one concept, and that's the concept of current, electric current. We've already learned about voltage. Voltage is how much force the electrons get pushed through with. Current is the measure of how much current is, or how, you can't define a word with the same word. How many electrons are flowing. And it's not measured in electrons per second, it's measured in coulombs per second. It's measured of charge flow. Coulombs per second. And the more common unit of current is amps. How many amps are flowing?
Are amps just coulombs per second?
Yeah, that's what an amp is. Yep.
Like the
So you need to know two things in order to be able to answer an electrolysis plating question.